I first met our next speaker when she and my wife were working in the same lab. She then became the TA for my class, and she's been a wonderful TA. And despite her long history of killing even office succulents, she's managed to keep an orchid alive since May of 2019. Please welcome Monica.
All right, here we go. Hi everyone, I'm Monica, and today I'm going to be talking to you guys about how to prepare and teach an R lesson. So why are we talking about teaching at a conference where most people are in industry, perhaps not in academia, and thus, say, not having to teach a programming course to undergrads? Well, nobody is born knowing how to code. All programmers have to start somewhere, and we are all constantly learning, including at events like this. If you ever find yourself responsible for training someone else to program, from 5-minute informal tutoring to an entire programming workshop or course, both you and your learners will benefit from you knowing how to teach. In addition, teaching well promotes equity. While we have a long way to go towards equal access and representation in technical professions, any chance that you get to teach well is a chance to level one of the many uneven playing fields that people might encounter on the way to a career in data science or scientific computing. So if you teach effectively, you can do one small part to help lower those barriers. So, by the end of my talk, I hope that you will be able to compare principles of backward lesson design to principles of good coding. Apply backward lesson design to outline objectives, tests, and content for an R lesson. Implement formative coding assessment check-ins to check learner understanding during a lesson, and to describe benefits of narrated live coding. So, first, let's get into backward lesson design. But we're going to talk about code first. When we're writing code, be it a helper function, a data processing script, or perhaps an entire package, there's a common logical order that we follow while doing this. First, in coding, we define our function output. What is it that we want our function, or whatever it is we're writing, to do or to produce? Then we write our tests for that output. How are we going to know or be able to verify that our code is doing what we want it to? And finally, we write the code. We can only write the code after we've defined what it's supposed to do and how we are going to know what it's supposed to do. If you were to start writing your code before you did those other two things first, then the code would just go nowhere. Backward lesson design takes that same logic from coding and applies it to teaching. So if the usual method of planning lessons starts with choosing activities or demonstrations to use and then building a lesson around that, then if that's forward design, then backward design in lesson planning involves the following steps in the following order. First, we define our learning outcomes. What is it that we want learners to come away with being able to do? Then we define our evidence of learning. How are we going to know that our learners have learned what we want them to? And finally, after we've done those two things, we build the lesson. So, you'll notice that this looks a lot like the logical process of coding. Both coding logic and backward lesson design aim to answer the following questions in order. First, what should our code or our learners be able to do? Next, how will we know that they can do it? How will we verify this? And finally, how are we going to equip our learners and our code with the ability to do what we want them to do? So you already know this logic. Lesson planning is in this way conceptually similar to writing code. You don't need to acquire a whole new knowledge base from scratch in order to be able to plan a lesson in R. You only need to learn how to relate concepts from coding logic to backward lesson design. And that's what we're going to do for the rest of this talk. So next, we're going to dig more into each of these 3 steps of backward design as they might look in an R coding lesson, starting with defining our learning outcomes. So defining a learning outcome or a learning objective is conceptually similar to defining the output of a function, a script, or an entire package that you might write. It is the answer to the following question. What will learners be able to do when the lesson is finished? Answer this question, and that answer is your learning objective. So when we're writing learning objectives, the most important thing for us to do to make these objectives effective is to be specific. You have to be specific when you're spelling out a learning goal for it to be the most effective. Just like it's harder to write a function when you haven't delineated what you want it to do, it's harder to prepare a lesson when you haven't outlined exactly what you want it to teach. For example, if we have this learning objective for a lesson that teaches novice R programmers to be able to manipulate and explore some data in R, we could start with this. It does outline the 3 packages we expect learners to be able to do, but understand and explore data is kind of vague and doesn't actually say specifically what skills learners will come away with. If we look at a more specific version of this, you'll notice that it is, first and foremost, longer than the first one, and second, is much more broken out relative to the first one and has specific skills that learners will be able to do, like reshaping data, generating summary statistics, and making exploratory scatter plots. So next I'm going to talk about some tips that you can use to make your learning objectives a little bit more specific and ideally more effective. So the first thing you can do is to use active verbs in your objective. In general, if you start with a framing like, learners will be able to use X to do Y, that'll generally get you in the right place. And next, if you're focusing on teaching functions from a specific package, name the package. And further, if you're focusing on just a few functions from that package, name those functions. And finally, more verbose is generally better for learning outcomes because that'll help you be sure that you've explained with enough detail exactly what skills learners will be able to acquire. But of course, don't go overboard. And as an aside, you'll notice that I opened this talk with a set of specific active verb-based learning objectives in order to try to model the types of backward design that you can use in your teaching in this talk. So now that we've talked about the first step, defining our learning outcomes, we're ready to move on to defining evidence of learning. So how are we going to determine that learners can indeed accomplish what the learning objective says that they can? Again, in programming and in teaching, we must test to confirm whether learners have accomplished our learning objective. So in coding, this can be as simple as running your code multiple times under different conditions to make sure that the output looks right, or as elaborate as a full unit testing system. So testing learners' coding can happen in a variety of different ways, from live fixing your code in front of the person helping you during informal tutoring to coding an entire final project for a semester-long class. In every case, the only way that we can know that learners have reached the objective is by testing their ability to demonstrate it. So, of course, the final assessment after a lesson is essential to determining whether learners have met the objective. But by design, it happens at the end of the lesson. What if learners make a critical mistake on the final assessment that shows that they haven't actually reached the objective? At that point, the lesson is over, and you don't have any time left to get your learners back on track. So this is where formative assessment comes in. When you're teaching, you have many chances to assess learning before the end of the lesson. Formative assessments are frequent and specific tests of learner understanding during teaching. So formative assessments in teaching are like unit tests in coding in the following ways. First, formative assessment and unit testing both identify bugs in learner understanding or code functionality. And next, both of them are built into the process and should happen in the process of learning or in coding as opposed to just at the very end. And next, both enable in-the-moment debugging so you can check learner understanding or code functionality like while it's going. And next, both encourage more effective lesson style or coding style. And finally, if a formative assessment or if a unit test fails, it's on the road to your code or your learners getting it right the next time you run it. So next, we're going to talk a little bit about how to implement these formative assessments. So if we think back to the example lesson that we started mocking up teaching some functions from tidyr, dplyr, and ggplot2 to explore data, we can look at an example. So the function chains that are encouraged by tidyverse style lend themselves really well to formative assessments. Formative assessment check-ins can be built into a lesson after every function in a pipe chain is introduced. So if we look at this pipe chain, let's say that we're teaching towards the second objective where we calculate means and standard deviations of the lengths and widths of flower parts in the iris dataset. Suppose we've already taught and checked through the 3 verbs that you see here in this pipe chain. Then, perhaps we have just demonstrated to learners how to use named functions inside across and summarize to generate summaries of multiple input columns. So to check understanding, we might give a prompt like this. So here we've given specific instructions to write a single line of code from scratch to summarize iris long, that chunk that we've already made, in this particular way. So notice here that our check-in question explicitly asks learners to produce a single line of code only to do what we're asking them to do. We can also, instead of asking learners to write out code from scratch, we can give them a line of code that they need to edit to produce the desired outcome. So this can also help us test bite-sized concepts. So you can see here that we're asking learners to change the code that we have to get the correct suffix on their summarized outputs. So while this requires learners to generate less code from scratch, which is sometimes what you want, sometimes what you don't, it can be faster to run during the lesson, which is the main benefit. So running formative assessment check-ins of single lines of tidy code is really handy for the following reasons. So first, learners get a natural pause after each concept is introduced, which helps them solidify their understanding before adding on more information. And next, when fewer lines of code are tested at a time, ideally one at a time, if different learners make a mistake or have a misconception, their errors are more likely to overlap with one another. That means that you, the instructor, when you're helping people, can demonstrate an error or fix it in front of the entire group instead of having to go around one by one and help each person individually. So that helps you go faster, and it helps your learners not have to sit and wait for you to help someone else. And finally, each check-in question can be repeated until every single person gets it right. And that ensures that when you get to the next function, you're confident that everyone understands everything that you've gone through so far, so you won't have to do catch-up later. So, all the check-ins that I've shown you before are all written as either free response or edit the code prompts that do involve typing in console. In small groups, this is generally the most flexible way to implement these formative assessment check-ins, because if they can write the code that works, then they've hit the objective. But this does require that you, the instructor, either trust that everyone has run it correctly or visually go around and check everyone's code to make sure that it actually does what it's supposed to. And this can be time-consuming if you have more than a few people. And there are other methods of formative assessment that, while less comprehensive, can scale a lot better to large groups. One of my favorite of these is a multiple choice question. So for example, I can ask a question like this, with 2 options, each corresponding to a specific R Markdown chunk that I'm going to show a screenshot of. So, for example, learners would have to vote using an external polling app, whether chunk 1 or chunk 2 is going to return the output that is requested in the question. Then I, the instructor, or in this case you, would be able to look quickly at the percentage of responses that your learners are making and be able to tell what percentage of learners are choosing the correct answer. And when written carefully, multiple choice questions are almost as good as free response. What I mean by this is that distractor answers, or the incorrect answers that you choose or that you show, can reveal specific mistakes and misconceptions almost as well as free response questions. If distractor answers are written to look plausible, featuring commonplace mistakes, maybe a mistake you once made in the past, then you know that if learners choose the correct answer, they're choosing the right answer because they think it's right and not because they've ruled out all of the other answers to be incorrect. In that scenario, someone could feasibly get the right answer without actually knowing why it's right. And so to that point, I want to say briefly, don't write trick distractor answers, especially those where you haven't actually taught or explained to learners why the incorrect answer would be incorrect. You want to make sure to test learners only on skills that you've shown them so far, otherwise it's a waste of time for them and for you. So, now that we've talked about how to implement assessment formatively during a lesson to check learners' understanding, we're now ready to build the lesson itself. So the nice thing about backwards design is that once you've spelled out your learning objectives and your check-in tests, ideally the lesson itself is almost done. Once you've laid out your assessments, you should be able to see exactly what you need to demonstrate and explain in order to equip learners with the knowledge necessary to complete the check-ins that you've laid out. So the core principle that I try to rely on when crafting lessons is to teach what you need to teach. No more and no less. This is kind of broad and covers a lot of things, so I'm going to break it down for you. First, it's important to calibrate to learners' incoming skill level. What do you think that learners should be able to do already before they start your lesson? Start where learners already are, so don't reteach stuff if you don't have to, and teach everything that learners need to know to hit your objective. And this means that you need to think through all of the prereqs and make sure that either you think learners already know them and you check it to be sure, and that you're teaching everything else. Next, allow your formative assessment check-ins to break your lesson into manageable chunks. If you have implemented the right number and the right scope of these check-ins, each of these check-ins should serve as the end to a bite-sized piece of lesson, about 5, no more than 10 minutes. And these bites are a good size for you because you get to take a break from talking and you get to check everyone's progress. And they're a good size for learners because they get to take a breather from new information so that they can solidify what they've just learned and practice it with the check-in. Next, teach less than you think you have time for. An instructor teaching a lesson for the first time is often likely to find that lesson just takes longer than you originally planned. And running out of time before you finish pretty much 100% guarantees that your learners aren't going to reach the learning objective. So finishing your content in time is key. And that doesn't mean go too fast. Generally, it means plan for less time and let things go longer. I usually plan for about 2/3 of the time that I know that I'm going to have when I time my lesson out beforehand, if I've never taught it before. And then it usually comes out right, but your methods may vary. And next, teach one way to do things. One of the great and terrible features of R is that there's often many different ways to code a particular problem. While some of these ways might be more verbose or less generalizable than others, sometimes you just get to 2 ways that really differ just on personal taste. For example, in the pivot longer chunk that I showed before, where we're teaching people how to pivot the iris dataset, there's 2 different ways to split the column names. One way is that we could use the names sep argument of iris in order to break up column names at the period. Another way is that we could use names pattern to use capture groups to break up the 2 sections of the column name. So in practice, there are valid arguments for using either one of these methods. Using name sep to split, as you can see, is less verbose, but theoretically is less flexible than if we were to use capture groups with names pattern, just in case there are future columns that don't all have the period, for example. Here we have to think about what is the learning goal. If the primary objective is to learn about the 2 different arguments that you can use with pivot longer, then definitely show the 2 and talk about the similarities and differences between each strategy. But if the objective is only to be able to pivot the data at all, and not necessarily to be able to tell the difference between these 2 specifications, then teach only the way that you want students to be able to do. If comparing and contrasting between 2 different coding methods isn't part of your objective, pick the one you'd rather students be able to do and stick with it. That'll be much less confusing to students and it'll save you time. So, now that we have talked about building the lesson, you're now ready to deliver it. So most likely, you're going to teach via live coding, whether it be standing up in front of a group of people and coding along with your computer projected to a screen, or a screen shared out to a large group, or if you're just one-on-one, coding on your computer next to someone who's got, say, their laptop next to you. You demonstrate the code example on your machine, and then learners follow along with what you've just done. So coding for an audience is a little different than coding for yourself. You have to be intentional. Even if the audience is just one person with their computer next to yours, intentional live coding can spell the difference between them following along with you versus not. The single biggest tip I can give for any live coding context is to narrate everything that you click or type. Like literally everything. Every word, every parenthesis, every quotation mark, every hotkey shortcut If you're clicking, say what you're clicking, where it is on screen, spell it out. This helps in many respects. For example, it helps learners orient themselves to where they are in the RStudio or whatever other coding window that you're using, especially if they're not super familiar with like where menus or panes or buttons are. You spelling things out helps them find things faster. And next, it helps slow your pace down as you're typing so that learners are better able to actually keep up with you, because more novice learners tend to just type code a lot slower than more experienced folks. And next, it helps model effective coding technique. For example, if you use a certain set of hotkeys as shortcuts to make your life easier, you want to pass that knowledge along to learners as well. And if you make typos while you're coding, if you can narrate out how you catch and fix those typos, it helps learners with a big implicit objective of learning to code, which is catching their own mistakes. And I do want to note that with live coding, of course, remember the lesson building tip from before to calibrate to your learner's existing skill level. If you know that your learners, for example, already know where the help tab is in RStudio, you don't have to say you're going over to the bottom right to click the help tab. If you do go over there, you can just say, I'm going to the docs, and then go and click. So you can calibrate how much you narrate to how much experience your learners already have, but in general, it doesn't hurt to err on the side of narrating a little extra. So finally, I'd like to go back over the objectives of our talk, or of my talk, now that we've gone through everything. So by now, I hope you are able to compare principles of backward lesson design to principles of coding. Apply that design to outline an R lesson from objectives to tests to content, and more specifically, be able to write and implement these short check-ins to check learner understanding, and finally, be able to describe some benefits of slow, narrated live coding. So, with that knowledge, thank you for your attention. I hope you go forth and feel more equipped to teach effectively. Thank you.